So before it's just US only. And in 2001, then they combined with Mexico and Canada, and then introduced the first North American specification. And since then, all the specification equations need to be converted to non-dimensional equation. You remember the unit system is slightly different between Canada and US. They use kips and and they use different units. So that's why every equation now it has to be non-dimensional. That's the history now. So start from 2001, then the first North American started. Specification started. And then it's been revised in 2007, and then where the first time Professor Ben Schaeffer and Professor Tillman Pickup, Professor Tillman Pickup is a student of Professor Winter. So they introduced to the Appendix 1, the direct strength method. So it started from that. So, so 2007 officially started, but they put in Appendix 1. So they not in the main specification, they put in the appendix. The main specification still, we still use effective width method. And then later on, I think 16 or I can remember, 16 or 12, they start, yeah, 12, they start to swap. So direct strength method now is the main body. And they move the effective width back into the appendix. So there's some significant improvement in here in direct strength method in America. Okay, so that is a brief history about AISI specification for cold form steel. And now we'll give you a bit of history about AIS and ZS 4600. So as I mentioned before, though the code is similar to North American specification, and the reason why behind it I explained to you already. And it's first published in Australia in 1974. And the second is still in 1988. Do you remember at that time it's just Australian AS. And then officially start from 1996, it joined by Australian standard and New Zealand standard. So this is actually start from here by Professor Hancock. He brought all the LRFT specifications from US and adopted to Australia. So IS and as I said that 4600 really started from 1996. All right, so then take a little bit of time, probably 20 years or kind of just 10 years. And the second edition is updated in 2005. And then now there's a lot of things happening at that time where he includes the new direct strength method as an alternative to effective width. And that is, I think this one, he brought it in Australian standard a little bit earlier than AISI. And then he put in a separate chapter. So chapter 7, it's just for design of direct strength method. So that is what's happening, and you can look at that. And now he increased the range of the steel. As I mentioned before, Australians, particularly blue scope steel, developed the technology for reduction process. So that's why they can make a very thin and high strength steel. So they can make a G450, 450, and 550. So now we officially include that in the standard here in 2005. And that allows you to use, to design for structural member, which is the thickness less than 1 millimeter. So this is something new, it's different with US, with AISI, because with AISI, in US, for some reason, they don't use, they still use normal strength steel, grade 300 for purlin or for structural, for cold form steel. But in Australia, we are using high strength steel for low cold form steel. So the grade now is G450 to G550. So that is new for Australia. So then, since then, back to 2018, you have a question? Okay. Good. So it takes about 15 years or something for Professor Hancock to propose standard to make a change. Just something to share with you. In Australia, when you make a change, you need to apply for big proposal. Not like in America, they are very active. Every 5 years, the committee do and renews and improve, incorporate the new standard. Very active. But in Australia, somehow, it all depends on Professor Hancock, actually. So he's the chair. So at that time, he convinced BlueScope Steel. They pay for the improvement or the update of the AS 4600 2018. So the last edition. So since then, there's a lot of research happening, particularly at Sydney Uni and John Hopkins, and of course a couple of work from Professor Madhavan and around the world. And we need to look at that and then try to update that one in the next proposal. So he talked to me last week when I had a coffee and said, "Oh, it's time for you to think about how to go through the proposal." And it takes about 5 years to make a new proposal. So I'm working on that. So hopefully in the next few years we see something new, some update in Australian standard. Okay, so as I mentioned, direct strand rules in 18 is updated, including the design for shear and combined bending in shear. Before that, in 2005, direct strand method just apply for compression and bending. And since 2018, then we can design for shear. And this is make me and our group very proud of, because it's all based on my PhD thesis on my group. So all the change in Australian standards is based on my group and my works for the last 15 years. And later on, I will share with you all the chapter, all the part Gs of American Standard AISI for shear, and every that chapter is totally changed by our research at Sydney Uni. So we're very proud of that. So in the history, totally the first time we changed everything, whole chapter on that. I will share with you what is that later on. Okay, so and then we combine, we introduce new direct strand rules for inelastic reserve capacity. So it's based on works from Professor Ben Schaeffer and his PhD student Sheffield in John Hopkins. So that included into that standard, and then now another interesting rules for design of a new type of connector. So I'm not sure you are aware of PAPs. Right, so I'm going to talk about that very thoroughly later on. What is PAP? So PAP is the new innovative fastener they used to punch into the steel to make the connection. So it's very powerful. It can driven into the steel like the thickness of 20 millimeter easily. So it can do it very quickly and very powerfully. So the industry introduced that into the market, particularly the company, you heard about Hilti, right? Hilti, Ramset, and all big company, and they're looking at that one. So PAP is not new, is applicable, it's been used for concrete or anchorage in the concrete and decking on concrete a lot, but for steel to steel, that is still new. So that's why they sponsor for us to do a lot of research at the moment to use the PAPs for cold form steel structure application. So at the moment at Sydney Uni, we start looking using PAPs in the connection around the shear wall, shear panel, stick on the hot roll steel. Because hot roll steel, the thickness is 10 millimeter or something. Screw is you're not gonna do it, right? And if the bolted they're taking a lot of time because you need to drill the holes and you need to bolt it, and that take a lot of time. So PAP is a new way to do it. So I'm gonna talk about that later on in another lectures on connection. So in order to design that, of course, you need a rule. You need rules to design that. So in the latest AS 4600 2018, we introduced the rules for that. So you can actually design those type of tabs in AS NZS 4600. Right, and then importantly, we also including the design for phi. So phi engineering now is you have equation to design for phi. I think the first time in cold-form steel design standard. So all those work is based on excellent work from Professor Mahendran. Probably you heard about him, right? He's a professor in Australia, working at Queensland University of Technology. So he's very famous on the work on phi. And then if you have time to look at that, you can search his name, and then there's a lot of work on phi. I think this is one of the very hot topic at the moment, the phi protection and phi design particularly for design code. So just share with you recently, we made a huge, not AS for NZ 4600. So we make a huge improvement on AS 4100, that's hot rolled steel. We haven't done it for many years. And then recently, it's been thoroughly reviewed. And we hope that we can put in into public review for next few months. So you might have a chance to look at that. So we make a lot of improvement, including introduce phi engineering, phi design in AS 4100 as well. So very exciting at the moment in Australia, particularly for hot rolled steel specification, AS 4100. So equivalent to IISC 360 in US. Okay, so I'm very fortunate. I was a part of the task group to look at to change some equation, but it's a big change, and I hope that I can have time to share with you in the future. But if you're interested, you can look at that. And then we put in public review for next few months. I will keep Professor Madhavan information, and then we can put it, because it's in public review, so everyone can access, so you can see what's new and what's been going in that space. Okay, so and one more thing news is in Appendix B now. We introduced the second order elastic analysis, and particularly very interesting is the first time we introduced advanced analysis in Australian Standard Code now. So those are very interesting way to design. So based on the direct design method introduced by Professor Kim Rasmussen in our school as well. So what you do now, just briefly about advanced analysis, you don't have to design on member base. So what happened now on any standard, you have to run structural analysis, right? And then you break it down into column, beam, or whatever component and design for that. So that is member based. And so all the rules in here based on the member base. You separate in column, beam, shear, and everything, and then you can design for that. However, the advanced analysis allow you to design for the whole system. You can build the whole portal frame or the steel structural frame and run FEI analysis, and you gotta design for whole system without having checked any single member. So it's actually something new, very interesting, and then and it's allow you to design that based on the standard, the new things in AS NZS 4600. All right, so that is probably another course on that. I teach in Sydney Uni. We bring that one into the curriculum in steel design, but so hopefully that you can do similarly in India in the future. Now, as I mentioned, I introduced you yesterday. So cold form steel made out of hot roll coil or hot roll plate. So they will fed into a series of roller and then make it thinner. And once it's get out of the series of roller, then it's getting thinner and stronger. But then they has to went to the coating to protect the corrosion. So there's a standard for coating. So in Australia, you need to look at IS 1397. The latest update is 2021. So there's a bit of new update in this standard as well. And just share with you, Professor Hancock is also the chair of this committee. So he provided me a bit of information. So this is all the coating in Australia, okay? So I'm not sure about in India, you guys have the jinglam coating? Okay, in here, right? But do you have aluminum one, AM?
Yes, aluminum and zinc.
Yes, yes. So AM here, and also is very exclusive for BlueScope. So we actually introduced that rule just for products of BlueScope in Australia. And other is based on the imported steel. But in Australia, we have one particular standard in here, rules for AM. So that is something new introduced in AS 1397. Okay, so this is the latest update in 2021 for coating classes. I'm going too fast, right? Yeah. Any question, you just feel free to raise your hand. I'm happy to take any question. You don't have to wait until the end, okay? Yes?
Zinc aluminum should not zinc, then about that aluminum.
This one?
Aluminum zinc and zinc aluminum.
There's some component on that, so they're metallurgical. So I'm not 100% how they work, but this is something really owned by BlueScope Steel technology. So it's a good question. I'll need to talk to BlueScope guys in Sydney and see what's different. Okay, I'll get back to you. Good. All right. So now we get to the detail now, or the technical aspect now. The question put up now, what are the differences between hot rolled steel and cold form steel? Of course, I introduced you yesterday, right? Cold form is very thin. They use thin section, so it's very light, very thin. And then this one is the one I showed you already yesterday, right? This is a material property, typical steel property differences between the hot rolled steel and cold form steel, high strength steel. So it's steel, so it's 200,000 of course, and 210 in US for young modulus. And go up here, have a flat top, and have this thing, this U stress, and then go up, and then you get a strain hardening region, and go to a FU on top in here. And you can see the hot rolled steel has the very large ductility. It's about 15 to 20% in here. Opposed on that, high strength steel, because the change in the micro scale, in all the crans and all the particle of the steel, then it makes the steel stronger. However, it will be less ductility, less ductile. So instead of just you and it keep going until here, and then they start to be nonlinear, not clear distant U point. So it just gradually go up in here about 10% maybe, and it depends on the grade. So with the G550, FY and FU probably the same, very close. And the ductility here is a lot lesser than the ductility of hot rolled steel. Okay, so normally in here is about 7%, and one can ask, what is the minimum requirement? Because if you design for steel structure, if it's very fractal, very brittle, then it's no good, isn't it? There's a requirement. So in US, I think is the requirement. The requirement is the minimum is 3%, the ductility. So that is we can apply the cold form steel in here. So the ductility actually a problem, not problem, but it's the consideration of when Professor Hancock want to introduce the rules for high strength steel in US, and this is one of the questions that they asked, what is the low ductility, how it's going to apply? And eventually we can prove to them it works. Yeah, it's 7%, so it's bigger than the requirement. So it works. All right, so thinner, and then they use the co-forming process, high strength steel, and of course the design of connection. There's a lot of challenges as well. I will share with you for last 2 lectures on designing of connection. And I did a lot of lectures on co-form steel, and there are a lot of questions on connection. So it will be an interesting topic to share with you. Okay. So then it's lead to, when it's very thin, then it's gonna lead to different filer mode. And there's some special filer mode that probably just existing in co-form steel, not in hot rolled steel, as you can see. And we can look at that later on. If you're not familiar with designing co-form steel, I'm gonna explain to you a bit about that one later on. So there are different filer mode than those on hot rolled steel. And of course, to connect them based on welding is slightly different because it's so thin and it's high strength. So welding need to be aware or to be focused. And bolting, of course, you need to design for different equation. And then there are other different filer mode. For example, pull out, pull over, and then tilting. That's the other filer mode that you normally see in co-form steel connection, particularly for screw connection. All right, so I will work through that one later on. And that's why we need to have a special design rules. So that's why in Australia we got a separate design standard for co-form steel. If you use hot rolled steel to design for co-form steel structure, it's not gonna be appropriate. So we need to yes.
What would be the strain range for this?
Strength? Yeah.
Strain range. You have marked the stress range, right? 400 and 700.
Yeah.
What would be the strain range in terms of
strain range in co-form steel? Yes, so in Australia we use G450 to G550.
Strain.
A strain?
Yeah.
Stress and strain?
Yeah.
Okay, the ultimate?
Yes.
Okay, so this one to that one is about 1.3. Yes, roughly 1.3. This one to this one is about 1.05. So very close. So FU and FY. With the normal strength steel, you know that it's because of the strength hardening is increased a bit FU. So FU is very important as you can wear to design for connection. Right? We use FUs a lot, not for more for member capacity, but for connection. We use FU. Right. So now another problem is because of the cold form process. So we make out of the strip and then you fold it into whatever section. So normally that is open section. So you make it C section or Z section or other. So it's hardly, not like hot rolled steel, right? You got a doubly symmetric section like I-beam or universal beam. So it's very popular in hot rolled steel. However, in cold form steel, you normally see those type of section because it's the nature of how it make. You make the cold roll section. So interestingly, the C section, for example, let me take an example here. So interesting because you see that very popular in the purlin system, right? In supporting the roofing, or even in the wall systems, or even the columns of the portal frame, they use C-section a lot. So the nature of that section is interesting because the central is right some here. However, the shear center is in here, a little bit offside. So whenever you apply the load, for example, this is the purlin on the roofing, you apply the load on the flange, because you screw in here. Then what happens is going to create the twisting. So we have to pay a lot of attention on design of that one, not just by bending, but because of that nature of eccentricity, and then it start to twist. Okay, so that is how we need to pay a lot of attention on those type of section. That's for beam, and then it's for column as well. So this is the singly symmetric section, the chain. So it tends to buckle in fractural in one dimension or fracture torsional. So in a combined buckle sideways and twist. Okay, so that is how it can buckle. So this is typically the failure mode that you might see in the singly symmetric equation. So they all well defined in the standard. You can base on that and design for that. Right, so this is what we need to pay more attention when you design for those type of section. Right, so this is something that I get back to the origin, the fundamental equation. If you're familiar with those, just something for you to review. But for those not familiar with the fundamental theory equation, so I want to just do it quickly for you as the review. So local buckling. So this is a test of the box column with the short column in our lab, in Sydney University lab. So because it's short, and that's why when you press it, it buckles in local buckling. And when you look at the cross section, you can see that it buckles in and out. So that is in and out. In the plate here, if you cut the cross section here, and when you move in, you can see that buckle shape in that plate here is the side function, isn't it? It's local buckling. And because it's local buckling, so the interline, the intersection here, the line here is still straight. It's just happening in that plate only, so that is local buckling. Okay, so that is very fundamental failure mode that you see in the thin section. Because if it's thicker, then there's no problem with buckling, right? It's just getting yield, and then it's squash. But because of the thin one, it buckles before it gets into the yield stress, right? So this is the nature of local buckling. Okay, so I will talk about post-buckling now. Now before that, let's just go back to very fundamental equation, Euler equation, 1D equation. So if you have one column and you press underneath under the compressive load, compressive stresses, so what happened? It's gonna go up to somewhere in here when it reaches buckling load, and then it suddenly buckle. It's gone. It's collapsed. And this is for the perfect column, but this one is for imperfect column. Not every column is perfectly straight. It might have a little bit of deflected shape in the beginning. So that's why when you apply the load, it starts to move a little bit, but then it's go up here and then it's approaching the buckling load. So with the column equation, very famous equation is the Euler equation. Everyone know about? So simply n square, pi square EI on R, depending the length, E and I, and N here is the failure, the number of modes. You can have one mode, two mode, or three mode. So it depends on the length of the column. All right. So that is 1D. So that's column buckling. So back into the Euler buckling equation. Now, if we have the plate, so plate you have two dimensions. One is B, and one is A, is the length. All right, so now you got a 2D problem, and the thickness is T. Right, so similarly, you apply the compressive stresses on top of that plate and bottom, and assumingly those four edges are simply supported. Okay, so then of course, everyone familiar with that equation, that curve, right? Right, so this is the K, is the coefficient based on that equation. So that is fundamental equation for plate buckling. So that is buckling stress. K is the coefficient for buckling load when it buckle. And of course, because this is plate, so you consider mu, right? So a Poisson ratio. And this is B is the width, and T is the thickness. Okay. So depending on the ratio between A and B, it means that the length and the width. Right. So let's get started with square one, where your A on B is 1. So you can see that the K is dropping down to the minimum, and that minimum case now is 4 for that cases. For purely compressive under that plate, and then with 4 H are simply supported. Okay? And then when you increase like 1.2, 1.3, it's going up. Then when it's going to 2 to 1, and it's going down again to second mode. But they have exactly the same kind. The buckling stress or local buckling stress is same, but it's just longer. And then increasing into a 3 now. So what it means to me is local buckling doesn't depend on the length. Right. It doesn't matter, 2 meter, 3 meter, it's just a multiple of the halfway in here. We call it halfway, all right? So it's halfway of the side function. This is the whole side function, okay? This is another number of the failure mode, okay? So this is how you design for plate buckling to determine the buckling stress for a column. For the plate in compression. And the solid line just connecting those one is very famous term was Gallon curve. You heard about that, right? So that is Gallon curve. Right, so it's very basic buckling plate where it's subjected to compressive stress. And then remember here, K is 4. And later on, we do a lot of calculation related to K, and then we can remember, okay, so with simply supported 4H and K is 4, right? So that is the purely theoretically based equation based on Timoshenko, okay? Now, post-buckling. So that is in theory. When you compress the plate, and then you expect that it's going to go up to sigma critical and it's just buckle. That is in theory. However, in the practice, when you test something, then you need to have to design for the boundary condition. So normally you have those platen at the end to press the plate. And because the boundary condition is slightly different between those edge in here, you can see the displacement here, the deflection is actually different at the middle and different with the end here. In the middle, it start to string a little bit in because it's buckle. So that gives us a very interesting observation. So instead of it going straight to sigma critical, that's what the theory that we learned. Instead of going here, it just fell, it's collapsed. So that is from the theory. However, it actually can carry more load. It's keep increasing, but it changes the slope. So it changes the stiffness. So it changes here, it loses about 40% or 30% up in here. Then it gets to nearly yield and then it fell. Okay? So the stress from here to here, that's quite big increasing or improvement in the strength. So that's what we call is post-buckling. Right, so the amount of stress that increased from here, that is the theoretical buckling stress from the actual buckling stress is increased about that much. So that is post-buckling, okay? Now, so that post-buckling lay a foundation for all our effective width method. That's we're gonna learn or we're gonna see in equation in the standard that actually based on that one. Right, so what happened with stress now, stress distribution? So instead of equally or constantly distributed as per the sigma critical that we learned, then it start to redistribute it because of the stress, and then it's going up. So the stress at the end is a little bit complicated. It's not constant. And right in the middle, when you cut in the middle of the plate here, you can see that it's really non-constant stress distribution. So the stress at the edge in here tend to increase, and this one is going down. So this is complicated, how to design for that, how to calculate the sigma critical for those stress distribution. Then von Karman is the first guy. He think about, it's too complicated, what we're going to do now. So his idea is to suggest that we replace that complicated stress distribution to another way to do it. Just very simple but constant, but to bit up here. So it means that not the whole element who carries the stress, it's just a bit of here, effective width. So it means that the one in here, we just remove that. So we just consider BE here, that is the B effective width, the width that it can be effective to calculate the post-buckling. All right, so that is come from von Karman, okay? And then what he proposed is he's gonna say, all right, so the plate will collapse or will go to the peak when the maximum stress here get into U. And the average stress here get into buckling stress, FOL. Then he just balanced those equations, then he got this equation. So this is very fundamental equation to start with effective width method. So now our BE is the sum of those two, BE on 2, BE on 2. All right, and BE of course smaller than B, of course, because we removed the middle one. And it's depend on FOL, that is buckling stress from the theory, from Timoshenko, and this is the yield stress, okay? So now we can see the relationship between BE and B based on von Karman equation back 2 years ago. Right, so now we got that one, and then we see how it been adopted into Australian standard or American standard based on von Karman suggestion. So he suggests this equation, then of course when you look at the graph in here, on the horizontal axis here is based on B on T. Yes?
What's the effect?
Sorry?
What is F max means?
F max is here, is the maximum at the edge.
Does that mean F wide or?
So he said that if we reach Fy and then is buckle. So that's why in here you can see that is F max in here. And FOL is that average one in here. Okay, so he said that one will balance with this one and equivalent to that one. So that's how it works. Good. Any question? Right, we keep going, okay. Now, start from von Karman equation where you can see B on T, there's slenderness. And here is the B on T, on B. Okay, so when it's very short, then B on B is equal to 1, is constant. So what does it mean? What's that? So it means that B is equal to B. Fully effective. Fully effective, doesn't buckle, right? It's yield and then it just spreads on. No problem with buckling. So this is actually hollow steel. Yes?
If you put Fy grading to B equal to effective width by whole width.
So BE on BU here. Yes, so back into here. So that is BOL, I think. Yeah. So it's no buckle in here. Okay, it's yielding. So yielding cut in. Okay, so this is all FOL in here. Buckling.
These two ratios are equalized. Fu by Fy, how come it is equal to B effective by B? It's a stress ratio to the dimension ratio.
Yes, okay. Now, we consider that is ultimate equal to Fy because we don't consider inelastic result yet. We said, okay, it's go up to F real and Fy is, because we idealize the hot roll steel, you know. We don't consider, what is that? We don't consider the strength hardening. So yeah, we go up and then we're just flat. So that's why you got this one. In some code now, later on, particularly for cold form steel, based on work of Professor Schaefer and Schaefer, then they introduced the inelastic reserve. So actually not one here, it's just go up in here, about 1.4, 1.3, to take into account that one. We can talk about later, okay. Right, so this is U cut in, and this is the von Karman equation. It's take into account the post-buckling. Right, that is Fy. And that is his equation, right? So, in theory, that's look good. All right, so he take into account post-buckling everything, but in the practice, then they scratch their head, say, oh, no, in the practice, our member is not 100% straight. There's a bit of imperfection there, so it might affect the strength. So we need to think about that, and especially with the slender one. Then you have a bit of problem. The factor that you need to consider is the residual stress. Okay, because the hot roll steel, whatever you produce because of the heat, and when it's cooling, then it will create the residual stress in the member. So we need to take into account those effects of that. So the standard say no, we need to factor down a little bit, because if you're using that, it's a little bit unconservative. So in Australia, no, this one, sorry, this is the buckling curve, right? The elastic buckling, this is all one. So you can see from here to here, it's post-buckling. The capacity up in here because of the post-buckling. Right, so as I mentioned before, because of the imperfection, because of the residual stress, then we need to adjust that. So the green line, or green curve in here, that is the equation in AS 4100 for hot roll steel to design for that. So just very simple, they von Karman and ship it down to factor it down. So that is the equation that you can find in Australian standard for hot roll steel AS 4100. Right, so that's it. So the question now, whether we can use that green one for cold form steel. What about cold form steel? What their behavior is slightly different with hot roll, as we know, right? It's very thin. Then it means that in this area where we're looking at the inelastic buckling, so this is purely buckling. This one is inelastic buckling. Then there are a lot of problem there because of the nature of the thin section. Then you need to consider the imperfection and all those effects. So George Winter, back into him. So he said, oh no, we're gonna propose something slightly different. So he actually shipped that von Karman curve, but he put that one down a little bit further to take into account all the imperfection. All right, at that range. However, he said no problem with cold form steel because the residual stress is not that bad, and when it's getting longer, it's actually good for von Karman. So that's why the blue one, you can see when it gets longer, then it's approaching the von Karman's equation. So it means that we need to do a bit of judgment to make sure that we can cover all that problem. All right, so this is the equation of the effective width method in AS 4600. So just give you a bit of review about where they came from and based on the fundamental equation in here. All right, any question? Good? Right, so let's move on. So those is two equations with different code, then we can design for that. All right. So basically that equation is on clause 12212 in AS and Z at 4600. Right, so that is the background and how we got those in standard. Now I start to walk you through the design of columns based on effective width method. Right. So there will be a lot of equation, but if you miss any equation, you can always look back in the standard. There's an equation number, so you should we look at that. But now, so let's assume that we design for columns and we can design for beam. Okay, so with effective width method, which means that we don't treat the cross section as a whole. We break it down as a series of elements. So for example, that is channel, we break into the lip, the corner, the flange, the corner, the web, and different elements there. And then we calculate each of element, then we can come up with the equation or the design equation. So for columns, you can see that because of the thinness of the section, then the whole section is not effective. So it means that just looking back at what we learned, there's some area that we need to remove. Okay, so that's the area that we need to remove. This one, it looks like there's no missing part in here because when you calculate, this is fully effective. All right, so the lip is good. Then we need to calculate here, it is good. Now, that's it for column. Yes?
In the lip, like, is there any particular lip dimension till when it is fully effective or it increases when?
Good question. There's all the equation for you to check whether it's fully effective or if not. Then if it's not, there is an equation that you can calculate to remove a bit of that. All right. But in that particular section that I choose here, is the lip is short and then it is fully effective. Good question. Right. So the compression is good. Not good, but it's probably easier to calculate, right? Because you just calculate and then you got a net area, effective area, and then you time with stress and you got a buckling load. Right. So that is simple. But bending here is a big problem because it's complicated. Because with the bending, you're going to see the top and the lift in here, of course, in pure compression, right? However, the web, top one is compression, then the bottom one, of course, in tension. And with tension, of course, it's so fully effective, right? It's still no buckle. So what happened is with the channel here, with the web, there's a remove area in here that you need to calculate. Okay. So looking at this one, when you calculate the capacity of bending of the beam, what important here is you have to calculate the section modulus, ZE, effective, right? So Z is section modulus. You need to calculate IX first, that is the second moment of area. Then you back calculate Z, which is the section modulus. And the problem here, you can see that cross section, if it's fully effective, that's simple because the neutral axis will be right in the middle because it's singly symmetric, right? But now because of that missing area, then the neutral axis needs to be moved down, to be shifted down. And then where is here, we don't know. Then what you have to do is you have to play the try and error. You have to try this, assume that it's there, and then do all the calculation and coming back. It's slightly different, and then you adjust a little bit and do another one. So if we're lucky, we can do a couple of loop iteration. But then if not, then you're gonna spend like pages to do until you get the correct position of the neutral axis. Okay, so I will walk you through an example how to do it, but just bear with me. It's going to be complicated, not complicated in a way, but it's going to take a long time. Okay, do we have a break? Okay, so I think it's a little bit long, so we might just take a few minutes of break and then we come back and we do an example. Okay. Good. We can talk while we have break, and then we can come back later. Thank you. All right. Hopefully, you just raise your hand if you're not clear in any question or any thing that I put it up. But I'm happy to stop and then answer any question. Okay. All right. So next part we will we'll go through the design example of two very typical structural component or structural member, which is the columns and beam. How to design those column and beam made out of cold form steel structures using the effective width method. All right, so I explained to you already what difference between the columns and the beam in terms of how to calculate the effective width method. So we pointed out like with the beam is a little bit challenging, where we need to we have to determine the neutral axis and then calculate the section modulus. Okay. Now we start to look at this example. So we need to design a columns with C-section, and that C-section has the dimension here. Okay, so the width is the D is the depth of the weft is 100 millimeter. It's very typical size of the wall stud when you design in the practice. Okay, this is in the wall. B is the width of the flange. So flange width 75 millimeter. The thickness is 1.5. And DL is the size of the lip is 16.5. So in this case, we use normal strength steel, Fy equal to 300 megapascal. Okay, so this is the effective length. So this is 2 meter column, right? So you got a LEX, LEY, and LEZ. So what is that? So L is effective width, effective length, where it's buckled in x-axis, y-axis, or torsional axis. Okay. So we're going to talk about those few three buckling mode later. Okay. So this is, we assume that the both ends are simply supported in terms of the flexural. So it means that the LX is in X, okay. So LX is 2000, the whole length. But LEY here is 1000, it's half. You know why it's half? That's right. So normally in the column in the wall system, you have another two hook, or what we call is knocking, just to attach that. All right. So when the knocking come in, they actually stop that buckle shape into half. So that's why that one will be reduced to half. So with the introduction of the knocking, they actually increase the capacity of buckling in that one, in LEY, not LEX. LEX is buckle outside, there's nothing to keep it. But inside, this way, there's two knocking. All right, so that's why it's here. And this one is a little bit hard to understand, but that's why. This is the torsional length. So what effect of the torsional length is depend on how you weld it to the cross section on the top. If you fully weld it, then that one will be reduced to half. But if you just push that one and it's allow warping, then that one will be the full length. All right. So we just accept those one as the elastic effective length of the column with respect to buckle this way, LX, this way, LY, and this one, LEZ. That's correct. All right. So there's three pure mode that we deal with. Other than that, we need to calculate the position, where is the location of the shear center and centroid. So of course you can do that with ThinWall 2 program that I think Professor Madhavan sent to you already, and hopefully you have time to download and start to play with that. Yes?
Can you explain a bit this LAX, LAY, LZ, because I didn't get this.
Okay. Right, so do we have something to draw? Okay. This one, is it? Okay, can. So if you have the channel section, you see that? Okay. So it's in the wall, right? So this is X, this is Y axis, and this torsional is X. The torsional is the twisting, okay? Now, in the practice, you normally have another channel. Sorry?
Major in x-axis is X.
Okay, this is major. X, Y, and Z. This is Z, okay. Yeah, sure. So imagine this is the column in the wall system, and normally you have another channel section. It goes through here. And that one side, and another side is go this way. Okay. So in terms of buckling, the knocking here will stop that buckle into half. Right. So instead of this, it's going to buckle like this one. In terms of y-axis. Right? However, in x-axis this way, it buckle this way. In x-axis this way. Okay? Because in nature, you don't have anything to stop that one from x-axis. So that's why in terms of LEY here, because the presence of those two, you actually reduce your halfway length. So you actually have the column, but just buckle about y-axis. It doesn't have in x-axis. Right? So that's why LEY reduced to half, but this one is still. LEZ is a little bit hard to understand, but then it depends on the condition at the end in here, where you weld it to the top or the bottom, and when you weld it, then it twists, it will reduce the twist. All right, because of the warping. Now just accept that one, because it's take a little bit of time to explain in terms of the drawing. I will do it later on when we move to direct strength methods. I will show you why LEZ is 1000 reduced to half, depending on the warping displacement. All right, so it's another term for you to learn when you talk about cold form steel. Anyone familiar with warping? Yes? Yeah, I'm sure that you familiar. Anyone? So warping is another displacement. It's actually the longitudinal displacement due to the twisting. When it twists, the cross section will warp. It's going to go up and down like this one, you know, the cross section. So what I mean is, when you twist, the cross section will go like this one. Sorry. Okay, you see my drawing? So it means that this is the same cross section, but because of twisting, this end will go up, that one may be going down, that one going down because of the twisting. Okay? And those warping, those displacement, we call it warping displacement. So then when you welded this one, in here, what does it mean? You fix that one. It's like the column, you fix that. So it means that it will somehow helping for the torsional buckling. Okay, so that's why warping will influence this one. All right, so it's a little bit more theory on the cold form steel, but I will introduce later on. Okay, so now it just see that you have 3 different failure mode. That is pure buckling mode. This is buckling about X, buckling about Y, and buckling about torsional buckling load. And then we calculate. Right, so the reason why we have to make that section a little bit different with this one, the difference is here we make it a square one. It's not a rounded one, as you can see. In the practice, you have to roll it, and then there's an internal radius in here. So normally R here is about 5 millimeter for the minimum requirement. If you make it very sharp, as we discussed with some professor here, then it might break at the corner, right? Because of very high concentrated stress, and it might crack. So you need to have a minimum requirement of the curve in here, what we call is internal radius. All right, so this is a practical actual section, but when you calculate the shear center and centroid, then if you calculate by hand, that is challenging, right? You can do it by using ThinkWorld that I sent to you. It's very simple. You put that one in, click the button, and the program will tell you where is the shear center or where is the centroid. But you're not always having the ThinkWorld 2 or the similar one is CSSM from US. Then how are you going to do it? So in standard AS4600, you actually can calculate the position of shear center or centroid, but you have to assume that is the idealized section with the square corner. All right, so this is a square corner. Then we can calculate that one. So first one, we need to determine, or we need to know where is the location of shear center and the centroid. And then based on that, we can calculate different, yes?
The dimension same for square corner?
They're very similar, B in here, but just the square here. Yeah, so B here is still the same, 75, but this is square. Yeah, instead of we have this one. So that is the only thing that we assume to make it idealized so we can design for. Right now, first step, we need to calculate the major and minor axis, second moment of area, Ix and Iy. Okay? So based on that geometry, with all the dimensions that you can see here, we can calculate R. And when we have the internal ratios, we can calculate the R plus with T on 2. So why T on 2? Because you consider in the center line of the thickness, right? So in here, you got R plus with T on 2. So we're gonna calculate the center line dimension. So we can calculate U. Yep. The U here, the length of arch, yeah, the length of arch we can calculate, and then from that we can calculate BF. So BF is the portion here from this to here. So that's why you got B, you minus with that 2 corner. You got B, the flat one, the flat portion. Okay, B, then you can calculate BW, that's the flat portion of this one. You got B minus 2 corner, okay? It's simple. And BL, you calculate this one minus with the corner, and then at the end you calculate the full area, the area of the cross section. So you can calculate that one. All right, very simple geometry calculation. Now next one, then you based on our structural analysis or structural mechanics, and we learn we can calculate easily the Ix. It's the second moment of area about x-axis, okay? So remember in here, we calculate about x-axis, major one. All right, so this is x-axis.
So can you use line element concept here to calculate the inertia? Line element. The
I think it's just based on structural mechanics, so whatever you do, you can calculate.
inertia equal to the length may not be high because thickness to the power of q. The inertia may not be high. So that could be omitted in the calculation of q. So taking all the flanges, lips, webs, borders, line element.
Okay, line element, all right.
In omitting the thickness, only taking the length of the element.
I think somehow in here, because you look at the equation in here, then there's some I in here, you ignore the thickness because it's too small. I'm sure that in here, in here, you check that one. So, gonna be, okay, it's actually in here, so you can see that. Very small as we ignore the thickness. You got it? Good, we move on. Right, so then based on that, we can calculate XC. And then we calculate EY. Similar procedure to calculate. You got all the element, you got all the area based on structural mechanics. You can calculate the XC is the distance between central to the center here. Then you can calculate IY. Okay. And then importantly here is the J. So when you design hot rolled steel, normally you don't pay attention a lot on J, right? So what is J? What's that? Torsional. Yes, yes. So it's related to torsional rigidity, isn't it? So torsional. Right. So J here, and then related to J is IW. Right. So when we talk about bending, we talk about second moment of area. IX, right? IX, IY, and then Z is torsion. And torsion, very important, and equivalent to that is IW, which is the warping constant. Okay? So we're gonna have that later on. So with that one, we can calculate IX, and then we calculate MS, then we can calculate the distance from centroid to the shear center. All right, that's very simple, straightforward, but a lot of equation, but it's very straightforward. You just follow that, and then you can work it out. So
About shear center, IXS.
you got it? Section mode
First calculation.
of the square one, of the square. You remember we need to calculate the shear center. We have to use the idealized square section. So S here is for square, and IX is the one with the rounded corner. This one is, we assume that is square, 90 degree, and then we can calculate that. So this is, you see that, the square one. So slightly different with the previous one. Yep, this one is for taking into account the rounded corner as well. Right, so those equation is from standard. You can look at the appendix, AS 4600. You can do it, work it out. So in the practice, normally in the company, and engineer just put that one in Excel file or something. You can drop in the section. You can calculate that. Right, now we got shear center, we got centroid, and what next? Then we can calculate the distance between the shear center to centroid. Then we have the equation to calculate warping constant, IW, okay? And then from that, you got this RY and RX here based on this equation, square root of RIY on A. A is the area, total area, okay? And then from those two RX and RY, you plug into equation, you get RO1. So this is how you do it, okay? Very straightforward. It's just here, just rearrange, put the number in, and then you get that. This one, it's just based on this definition.
It's a radius variation.
Yeah, that's right. So this IX, IY on A plus with the distance between the shear center and centroid.
Radius variation about the shear center, sir.
Sorry?
is it a radius of variation about the shear center, sir?
Yes, yes. So
To
that,
which I is XZ is effective.
you mean to put the S in here?
Is it a radius of variation, sir?
Yeah, yes, yes. Based on the that equation. Yep, yep. All right. Any question? Good. We move on. So very simple, right? We got that, and what else? Then we calculate the critical stress. So in the standard, this is how you calculate. This is the column curve in AS 4600. So you can see this is the slenderness depending on the ratio between Fy on FOC. And the FOC here is the buckling load where it fell, all right? And we can talk about that, how we calculate later, okay? But you can see the more you go to the right, the more slender it is. So it's more buckle in elastic buckling. When you go up here, close to 1, it means that you're approaching the yield. All right, the yielding in here, and in here, there's inelastic range. So it clearly shows in your equation. From 1.5, this is the ratio, lambda c, to here, then you need to use that equation. Okay? And from here, when lambda c greater than 1.5, you use that equation. That equation, in here, you see that is Fy, is yield stress. And lambda c is based on that, the slenderness. And the lambda c is square root of Fy, is a yield stress on buckling load, at FOC, the elastic buckling load of the column. And what is FOC now? We need to look at the failure mode. So this is the singly symmetric column, C-section. So not normally, there's two possibilities that it buckle. Okay, when you have the column, you see that. All right, that's good. That's good to demonstrate how it works. So, because you can see here, X is strong axis. We can say that strong. It's stronger to bend, right? And Y axis, because the small flange, it's very easy to buckle in that axis, so we can call it weak axis. Okay. Now, that's why they have to put the knocking in here to increase the buckling capacity, because if you don't have that, it's just buckling, go to the weaker one. So it's Y-axis. Right, so that is the fundamental buckling, like all the column here. You can see that is X-axis, that is Y-axis, and L here, this is L effective. Okay. Back into this one, you can see because Lx in here, you don't have anything to stop that. It's one half a way of sine curve, so L is equal to L. So Lx in here is 2000. However, with Y-axis in here, it can buckle this way, Y-axis, but because of the knocking, sorry. Oh, good. Thanks. Because of knocking in here, it actually reduced our effective to half. So that's one now is 1 meter. 1 meter. All right. So that's why you can plug in the equation here is 1000 and you got the buckling stress in here. And the torsional is when it's buckled in torsion. Right. So those are 3 pure failure mode of any single member subjected to compression. But with the channel section, singly symmetric section, there's only 2 failure mode where you have the channel section and it's very long. Do you have any ruler or something? Just for me? Can I borrow? Any ruler, very flat and that I can demonstrate. Okay, that's fine. Yes, that's it. All right. So imagine this is channel section. Okay, this is major axis, very hard to bend. Right, this way. But this is minor axis. Right. So if the column is very long, when you push out one, boom. Sorry. But that is really demonstration of how the column reaches buckling load. Really, really buckle. Go to
Exceeds the yield of the.
exactly. So that's very sorry I'm gonna buy for you. Don't worry. Okay. So that really showing you this is buckle in y-axis because it's so weak. The y-axis in here. You can compare the stress in here. No, not this one. You know why it's going up? Because it's you got this guy to help it. So that's why this one going up. Right? But if you don't have this guy to help, that one I'm sure that it's going to drop a lot lower than this one. So that's why you break this one. Right. So that's why with the channel section, there's two possibilities. The one that I break the rules, then it buckle in this one. Then it's happening here. That is FOY. That's buckling stress. That's going to happen. However, this is when it's long. But when it's getting shorter, and somehow you got this guy to help. So you're pushing up the buckling stress of FY is bigger. Then it's not going to buckle in this one. But then it starts to twist and buckle sideways in x-axis. Then that's what happened. Right? So that's why now it's clearly explained to you depending on the effective flank, how it restrained. Then it might falling in this case or this case. Which one is smaller? It will govern your design. So in the first case, I break the rules because Ly in here, we assume that there's no docking here, then it's a lot smaller. So then that one might control. But when we got this one, you actually have that from buckling about y-axis, then you have the combine between buckle outside and twist. So this is, you see that, the shape in here. So it involved in buckle outside, in x-axis, and then Z is twist. You see now, this is the combined failure mode. That is flexural and torsional buckling mode. Right, so now you have another term that you understand now. With the singly support, a singly symmetric column, there's two possibilities that it might buckle. First is this one, where you have very small or lower F or Y, or this one, where you have the combined action or combined flexural torsional buckling failure mode. All right, so that's one. So simply plug in that equation, simply plug in the equation. Now what you can see now, that one is 300 something megapascal. This one is 1000 because the help of this guy. So it's gonna buckle in flexural and torsional, okay? But flexural, remember, this way, our plan, not this way, because this way is good already, okay? Flexural and torsional. All right, so this is the weakest, the FOC now. So we simply choose the smaller one. And then we got FOC, then we put that in this equation. That slenderness, and we can calculate the lambda C. And from lambda C, now we compare with 1.5, it's smaller, then we apply that equation Fn, buckling, critical buckling stress. So that's what. Right. So now we know that this is the buckling, critical buckling stress of the column. 13, right? So what does it mean for me? Compared to what? U stress. So what is this U stress in here? 300 something. I think that's one at the beginning we say we choose the normal strength one, right? 300 megapascal.
It is 300.
300, right? Yeah, so we choose the normal strength one in here. So the critical buckling stress now 213. So what does it mean to me?
Before hitting partial buckling.
Exactly. So it means that it doesn't get to maximum. You know, they can actually carry more load. But if you want to carry more load, then you maybe have to put some knocking the other side to push that one up, to push the FOC up. Then you can get the full capacity, right? But no, in the practice, you're not going to put in here against a wall to stop that one from buckle outside. We have to accept that and move on and design for that. So that's it. We have to work it out Fn. And now we need to calculate the load, buckling capacity of the load. So we have stress. How are you going to calculate the load? That's right. Very important in here because the whole section is not working fully effectively. Then we need to calculate the area, the shadow area in here. We have to remove those what we call useless area where it's not effective. So our calculation now, we need to calculate AE. Of course, AE will be a lot smaller than A. It's a cross section because we're going to remove that area. Okay? So that's what we're going to do next. Right, so as I said before, we need to break our section to a number of elements. So element is a lift, flange, and web, and the corner. And then we just calculate step by step each of them. And then at the end, you're going to have all the number here. And then you can calculate AE, the area, the effective area. Okay? Right, so effective width. Now, we come back into the fundamental equation at the beginning, right? So this is the equation, and then this is the equation in our standard based on winter curve. The winter that I showed you before, so actually that curve, right? So this one is for calculate BE. Now, in this one, you need to calculate F critical, right? And F critical is buckling stress, okay? And with buckling stress here, we have to base on K. Remember K is coefficient. And what is K for plate for simply supported? 4. Now you remember, okay? 4. So 4. Okay, so now K will be varying. It depends on the condition, boundary condition, and how it works, okay? Now, in here, if you consider, you remember when you compress that one, the lift will be in pure compression. And the lift we consider as an element, the plate. So if you cut the lift, okay. Okay, so if you put a compressive here, you cut the lip in here, you with me? So what happened to that plate?
One side is supported, another side.
3 edge in here is simply supported, but this one will be free. So by not just calculation, but just observe that it's going to be a lot lower, right? The kV is going to be a lot lower. So with the kV for that is 0.43. That is basic number for kV. So depending on the stiffness, the boundary condition that we do here, we have different kV. So the standard, Australian standard, there's a table. Depending on that, you can look it up and then you choose your K, or you calculate the K. Okay? Right, and now that's what I'm talking about. Is depending on the stress distribution, the cases of stress, and the simply supported or built-in, depending on the condition of your boundary condition, and you got different K in here. And everyone know about bending, right? It's 23.9, okay? Because of bending, you got a bit of compression here, tension in here. Of course, it's gonna be a lot higher than pure compression. So this one, and this one is the combined action, combined bending and shear, and based on these cases, you can calculate the K. So this is just give you a bit of upper bound and lower bound. So this case is the worst case, where the lip, you got one side, one edge is free, then it's more. This is with the web. So it means that 4 sides are simply supported, is 4. However, with the flange, you can see with the flange, it's interesting. This one is hard to consider as the free edge, right? You got a little bit of stiffener, make it a little bit better. But it's not giving you the full support, simply supported. Then the flange in here, the K that you calculate, it has to be somewhere between 0.43 and 4, right? So that is why you calculate in here. So it just explains to you how it works. Right, so now, as I say, if the flange, then you're gonna calculate somewhere around that number, between that. So it's partially stiffened or partially enhanced by the lip. Okay, so now we keep going. Then now we isolated the lip only. You coming down, you break it down here and you calculate. So first is you calculate the dimension. D, you divide, you minus with the corner, then you got that. So 10 millimeter is from here to here. You got it? So that plate, and then you calculate the buckling stress with the D is the one that you just calculate, and K here is 0.43. And then you can calculate the buckling stress of that member, that element. Get it? And then from that you can calculate lambda. So lambda is now its slenderness and square root of F star on FCR. That is buckling stress that we calculate here. What about F star? That's the one that we just calculate, the Fn. Yeah, it's not going to 300, yes, because of the flexural torsional buckling come into that equation. So that's why F star here is 213 or something, right? Now, if you have fully restrained, you have the column, you put a lot of knocking, so it's not gonna buckle in flexural torsional buckling, it's just buckle in section. Then F star now is 300, the Fy, all right? So now you understand, right? The section capacity and member capacity. Okay? Member capacity is taking into account the length, taking into account the boundary condition, the help of the knocking, and then with the member capacity, the buckling stress not going to the maximum because of the, as I say, the effect of the length, effect of the boundary condition. Right, so then you calculate lambda, what else? Then you can compare, and then you plug into each equation, and then you can say that the lip is fully effective. Right. This case, the lip is fully effective. But if that one different, then in standard showing you if it's not fully effective, you need to calculate this equation, and then you work it out the effective later. But this case, because we choose that section, the lip is small enough to be fully effective. Get it? Right. So now we got that fully effective, no problem. Then we look at the element 3. Element 2, the corner, of course, they're all effective. Very small area is effective, not gonna buckle in the corner, right? Now, the next one, we look at the flange. And the flange is in pure compression, constant compression. But I explained to you before, the K is somewhere around 0.43 and 4. And then, of course, the whole equation here, based on the standard, you got all what you want, B, BT on T, and you plug into this equation, you got S, and from S, you compare with B on T, and then you plug into this equation, you can calculate K. And K is now, you can see, is 2.8, somewhere in the middle, between 0.43 and 4. So that's showing you what the effect of the lift on the buckling coefficient. Right, so that's it. Then once you do it, then you can calculate the F critical of the flange. And K now is the 2.8, something that we just calculate. Right, and then you get buckling stress, and you got a slenderness lambda, and then Fn here, as I said before, is equivalent to the critical stress that we calculate. Then you can calculate rho here. Rho is the percentage of effective width, right? BEF is rho times with the full width of the flange. So by doing this one, you can see here about 84% of the flange is effective, not 100%. Okay, so that's why you got a BEF. So this is the area that effective. So this is about, so 84%, 85. So it means that here is about 15% area we need to remove. It's hopeless. Okay, so that is how we calculate the flange. And in this one, interesting, this is just about the K in here. That's we need to pay attention. And K, because it's somewhere in between, then you calculate that. Any question? Yes? Element 2 is the corner.
Flange.
Yes, the flange is the tree, element 3.
Previously.
Yep. Yep. This is flange plane.
So what is this?
What is, sorry?
Yes, yes.
S just equation based on this one. We got E, we got F star, we calculate S. It's just,
Limiting W relations.
yeah, it's limiting, it's based on here, you calculate S, and from that, you can compare with B on 2, then you can see whether it's fully effective or you can calculate this one.
Thickness limit is expressed as S.
S in here, S just depend on E and critical stress, the Fn. It's just another term that you calculate S. It's not, I don't think it's any meaning here. It's just S to calculate based on those two. And then you plug into that equation. Then you can calculate IS and then you can calculate K. All right, just follow those equations and you can get it. Get it? Right, so now we get the effective width of the flange, and now we need to calculate effective width the web. And the web now is simple, isn't it? Because what I'm saying is simple because you can see here, so this is the web, and that is simply supported and simply supported because it's got those quite large flange to support that, and that is simply supported. So we can consider that element or the web element is simply supported in 4H in that one. So what is K here? 4. Right, easy. Huh? So element 5 is B is 91. Remember B is the flat one. You have to minus all those two corners. And you got B, you got T, you got D, you got everything. K is 4, as we agree. Then you can calculate buckling stress. And from buckling stress, you calculate the lambda is the slenderness. All right, from slenderness, then you can calculate rho here, which is the effective width equation. And now you can see with the flange, sorry, with the web, only 75% of the web is effective. All right, so that number will tell you. All right, so now we have everything. Now this one exactly the same with the other one, so we just double that. The flange is in pure compression and the lift. And then at the end, you just simply calculate the area, effective area. You add them all that area minus with the one that we need to remove. Then you get this equal, that's effective area is 318 millimeters square. And simply you time this one with the Fn, that is 213, remember the critical stress that we calculate. Then you get the NC, that is the nominal capacity of the column. Okay? So that is how you calculate the ultimate capacity of a column take into account everything about the member length, about the condition of the boundary condition, about the effective width and everything. All right. So when you change every little thing in there, it will change the capacity. For example, if you're adding one knocking in here, it changes the effective length, and then it will change the buckling stress, and then it will change FC, and then it changes everything. Okay? So this showing you how to design the column. Anyway. And of course, the next one is when you calculate the area with the yield stress get into the maximum Fy. As I explained to you before, you got all the help, you lateral restraint, everything. You make sure that you force our column just buckle in section. Doesn't matter along or whatever, because you restrain that one already. So that's why now we got AE here. That is based on the yield stress. All right, Fy, F star now equal to Fy, not Fn anymore. Okay, then you got that area. So you see that interesting? AE here with the yield stress smaller than AE of the column when it's buckled. Right? So very interesting. Huh? So it can change. It's not always the same. All right. So you have to make sure that you calculate the right cases. And some people, I taught students, they're doing this one and they're happy and they plug into the equation and that's it, done. But it's not right. You have to calculate the capacity at the critical stress, not about maximum stress. All right? But in our equation, for columns, there are always two ones. One is section capacity, is NS. It means that, yes? Yes. Yes, you have to calculate exactly the same process with M star equal to My, as F star equal to Fy.
Because when we calculate Fn, the previous we calculate for the whole process.
Yes. So you calculate Fn for the member capacity, right? It's related to buckling, nothing to do with the section, because it's related to FOC and it's related to Fy and FOZ, right? So it's buckling. So you take into account the member capacity. But when the member capacity buckle at the critical stress, and that critical stress depending on effective width or effective area. So that effective area you need to calculate. But as I said before, that is the case when you calculate the member capacity. But when you have fully restrained, you make everything good, and then you have to calculate section capacity. And section capacity, you don't have to worry about FOC or buckling, whatever. We just care about area. And what you have here is effective area at buckling stress maximum. And then simply you take this one times with Fy. Then you got an NS, and that is the section capacity.
Saying that cross section is effective only on that reduced cross section, then how will it be? Like Fn will be calculated through the whole section, not the reduced. You calculate,
I don't get your question. So you.
So like Fn, saying that A effective is reduced, like for the reduced cross section. Like
Yeah. Really reduce a bit, as you can see here and here. Yeah, you don't push it hard enough.
So if some of the sections are not effective, then how will you be contributing to the global like FN?
So that's why it's coming to all the IE, but with the critical stress in here at that stage. It's still not effective, but at that stage, at that critical stress, not a maximum, it's still there. So it's not clear in here because I understand from winter curve. So what he did here, he trying to calculate the buckling, the member capacity to take into account all the interaction as well. So the reason you have Fn smaller than Fs because you got a bit of interaction between local buckling and a bit of flexor-torsional buckling and everything there. So that's why it dropped down the buckling stress. Okay, so a little bit complicated. So that pointed out what you're asking is really good. Then should we do that one or we're gonna do it direct strength method? So it's gonna be a lot more innovative and advanced later on, then we're going to look at that. We treat as the whole section, we understand all the behavior, and we just plug into one equation. So that's the beauty. Where we know, and we learned this one, it's good, it works for many years, 60 years, more than that. Which is painful, isn't it? When you calculate how you calculate that, page by page, particularly with the bending, I'll show you later. Right, but this is just for the very simple plan section. And then if you have a multiple stiffener or whatever, then it's gonna, gonna scratch your head, how are we gonna do it? All right, so that's very good. Good question. It's related to how complex is that when you use effective width method. Okay, and maybe it's not really 100% accurate as well. We need to compare with testing as well. But this is how we did in the test. In the effective width. Right. So with section capacity, I told you before, we got AE for Fy, and just simply time with Fy, and then we got this is section capacity. So you can see section capacity here is greater than member capacity, which means that our section is not effective yet. It's not going to the maximum yet. It has some buckling or some member capacity in that one. All right. So in engineer, you need to make sure that that one is very similar. Then you maximize the section. You don't want to design some very strong section, but it just buckle in the member capacity. So that is how it works in here. Okay. Any question? Good. Let's move on. Right. So then eventually you need to choose the smaller one to govern your design. So in here, member capacity is smaller one, and you time with 0.85 is load factor for compression in standard. Then you get a capacity of the column. Now before I move on to the design of beam, then I just make a summary how you design for a column using effective width method. So first you calculate buckling stress. Remember FOX, FOY, and FOZ. Those three one. Then you plug into the equation, and then you work it out the critical stress MF. And then you calculate the effective width of the effective of area of the cross section at that critical stress. Then you can calculate the member capacity. And you have to do once again with the effective area at U stress. And then you can time with U stress, and then you get the section capacity. So that is NS. And once you got NS, NC, and then you compare and then choose a smaller one. That will govern your design. Okay, so that is all the steps that you need to do to design for a column using the effective width method. Now, I move on to the beam. Beam is a little bit more complicated, but the procedure is exactly the same. Right? We're going to talk about that later on, but all the bit that you do is same. So I take an example in here where you design a purlin C-section in a roof system, and we assume that the simply supported in here, and in here you got what is that? You got in Australia we call it raw bridging. Okay? Saddle in here.
Sag rod.
Or sag rod. Okay, you use that one. Right. So we use different terms. So in Australia we use that is a raw bridging. It's stopped from. You got that one as well?
Bridging member also.
Oh yeah, channel section or something. Yes.
Bridging member.
Bridging member. This is the road. Okay. Good. So everyone knows that the purpose of that road, right? So what is that?
About the minor axis.
Exactly. Okay. So when you talk about minor buckle, so what is that? Stop one from what?
It should be at the compression process.
Yeah. So the role of this one is stop the purling or the channel section here from fractional torsional buckling, or in US you call it lateral buckling. So similar term, but in Australia we call it fractional torsional buckling. This is a little bit long term. Okay. So the more you put that one here, the better you increase the flexure torsional buckling capacity.
So sheathing is connected to the member.
Yes.
Where it is stopped and is restrained.
That is the a little bit more complicated to design, but in this case, we're looking at upward. So when the wind blow into this one, it actually you blow the roof off. So it means that our bottom flange here, there's nothing to hold that. It's just this rod in here. So then you can check for flexure torsional buckling. Otherwise, if it's going down as a wind or snow or whatever, you got the roof sitting on top. There's no problem with flexure torsional buckling, right? It's hold that beam from flexure torsional buckling, okay? But now if you go uplift, there's a problem occurs because you have nothing to hold the bottom flange, and the bottom flange in compression is very, very sensitive to buckling, okay? Good. So the length of that beam is 7,000, and there one what we call is the rod bridging, or the rod that stopped in the middle. Right. So we need to design that cross section. You can see here that cross section is slightly different with the one that we choose before, but with the column you can see is the flange is a little bit big, right? It's 75 compared with, and then the depth is 100, so it's roughly 75%. That's for the optimization for column. But for beam, because it's subjected, the job of the beam is carry bending. So that's why you, in the cross section popular in Australia, we choose the depth is 200 and the width here 75 millimeter. So it's really about 0.33 or something. It's about 1/3. All right, the ratio between the flange and the depth. I shared with you before yesterday. In US, they actually make it a little bit narrower. So normally the flange is very narrow. It's about 20%. Some section is only 15%. So they maximize the capacity because the more the area away from the neutral axis, the better bending. Yeah, but then there's a lot of problem with the twisting and all that sort of thing. But that's how they make it the section in the US. But in Australia, very typical from BlueScope LISA. This is what we use in Australia. So we use 200 millimeter depth, 775 width. The thickness is 1.5. And we use high strength steel, 450 millimeter, megapascal, FY. Right, so we have only one rod of raw bridging, so to stop that one from flexure torsional buckling, okay? And that will relate it to FOY, FOZ, FOX later on, and it will relate it to LEY or LEX or whatever. So you're gonna understand a little bit more on that based on this one, okay? So when we put the lateral restraint, what L will be changing, then we can understand a little bit more. Right, so you can see here, LX, LY is 3,500 because of the lateral restraint here. But LX, LEX is 7,000, right? Because when you lift it up, there's nothing to hold it. But this one, when you buckle sideways, that's about Y-axis, then you got a bit of help. Okay, so that's why. Now, first is we do exactly the same. I don't want to spend not wasting, but I want to repeat again how we're going to do it. The procedure is exactly the same. You break the section into a series of elements, and then and then you based on the geometry, and then you can calculate the IX. Okay, and IX, IY. And then based on the idealized section with square angle, then you can calculate the shear center. You can calculate the centroid, not calculate the location of centroid and shear center. So exactly the same, you can calculate IX and IY, second moment of area, and this is J is the torsional constant. All right. Then this is the one I'm talking about. We have to idealize the section. It's a square one. Then we can calculate the location of shear center and the centroid. That is just all the calculation, and you can do it in the tutorial time if you would, you wish, and then you can do it. All right. So it's very simple now up to here, and now with the member capacity of the beam, the standard say you need to calculate the elastic moment capacity. Remember, FO here is equivalent to what in the column that we learned before? What is that? FOC. That is elastic buckling. So forget about, we haven't talked about everything in here. We just talk about elastic buckling. So MO here is exactly the same, equivalent to FOC, that is the elastic buckling moment. And elastic moment, you can see because this one is simply supported, subjected to uniformly distributed load. Then, of course, you got a bending moment look like this one, right? So the equation here, you got CB. And CB is what we call a shape factor of the bending moment. So it takes into account that shape of the bending moment. So in case, if you have, this is fixed end, you got a bit of poking moment here, then this one will change CB. Okay, so it depends on simply supported or whatever shape of the bending moment. And from that shape, you can calculate M3, M4, M5, and M max. It's just simply quarter, half, three quarter, and then maximum. And from that, you plug into this equation, and you got CB. Right, so in CB here, you put in here, then you can calculate F naught, the elastic moment, buckling moment. And in that one, you got RO1 is the one that we calculate before, and time with square one. And this is FOZ and FOY. Interesting here. So, what this one telling you? The buckling here. Why there's no FOZ? Why there's no FOX? Yeah, you're right. In here, because we talk about elastic buckling, and then we talk about elastic buckling, flexure torsional buckling. So imagine this is C section. Sorry, C section, this X, right? So if it's buckle up and down, not buckle, so it's the new one in here, so this X. And then if you don't have the lateral restraint, then what happens is going to buckle sideways and twist. So this one, Y. So they actually FOY here is buckle sideways, right? Because we call it wick axis, right? It's about this one. Y-axis here is buckle in wick axis. And in here, you got FOZ because it's buckle about that theta. Buckle sideways and twist. Okay? So that is the equation in here. So what we concern in here is elastic buckling of that one. Right? And now in the case, if you design, if you don't worry about the material, the boss say don't worry, you put, so instead of put one in here, you put 5 of them lateral restraint in the beam. So what's going on? Yep, that one, sorry. If you put 5 of them in here, the length in here will be reduced a lot. And when the length between the segment reduce a lot, that guys will increase a lot. Is that right? And then buckling load will be on the roof. It doesn't matter. It's not. It's elastic buckling, but it's not a problem. It's The problem now, if you put a lot of restraint in here, it goes to section capacity. The section now is going to yield, or if it's thin, it's gonna buckle in reduced to half. If you have 5 of them, what is LAY now? Will be 7,000 divided by 5, right? So then that one will be smaller, and then that guys will going up a lot bigger, right? So that is first one, and this one as well, related to the warping, okay? And that one will increase again, depend on the boundary condition. That's right. Right, so in the equation, you got all that you want. You got L, E, L, E, Y, you got L, E, Z, you got everything. You plug into the equation, you got F, O, Y, and F, O, Z. And then you can calculate the elastic buckling moment, simply, okay? And then you need yield moment. So you get F, M, Y here when it's getting to the yield. And then it's a section modulus time with Fy is yield stress. Okay? Get it? Right, so that is from this one. FO here. Right. And that is equivalent to FOC in the column, right? So what next? You want to calculate. You need to calculate Fn in the column. And we do exactly the same. We need to calculate MC. MC equivalent to Fn. All right? And MC, you can see you got a U on top, and this is the slenderness. Okay? So this is telling you whether it is member capacity or section capacity. So you can see the code telling you from 1 to here. It means that you have fully restrained in your beam, like you put 5 of them, all right? So then, no problem with member. It's just section capacity. But then if you reduce, you remove more, and then you provide less lateral restraint, then strength can dropping down because of the member capacity. It can buckle sideways and twist. And when it's closing here, it means that you got very long beam, and there's nothing to stop that. It just, when you push the load, it just buckles sideways and twist. And that close to M node in here. So it means that when your beam is very slender, without lateral restraint, it will buckle in elastic moment. Okay, so in this one, in here. Right, so you can see a lot lower than 1. It's probably here is 40% or something. So if you are a designer, this is not a good option, right? It means that that's why in the roof, you have to introduce the lateral restraint to stop that one. Otherwise, without what, you have only 40% of the beam because it's subjected to flexure torsional buckling. Okay, so then all depending on lambda. Lambda is depending M node and then My. And if, remember, coming back to the other equation where you have M node increasing significantly, then that one reduce significantly. So it means that it's going to the left. And when it's going to the left, so the strength will get into what? It means that now it's equivalent to the section capacity. It's not a member capacity. All right, so that's how it works. Very similarly to what we did in the column. Right, so importantly is we worked out the FC now. Right, that is the critical buckling stress of the beam, equivalent to Fn critical stress of the column. Right, so what next? Once we have FC, and then you can see here, is similar to column, right? FC is not 450 yet. It's close to the critical stress that we calculate. And from that one, then we can calculate the capacity in here, right? By take FC times with ZC extend here, all right? So this one, it make you remember what equivalent in column? Effective area of the section when it at the critical stress, not a yield stress, right? Right, now the problem here. This one I mentioned before, it's not easy to work it out, right? Because anytime you change the effective width, then you have to move neutral axis. And when you move to a neutral axis, you don't know exactly where it is, then you have to recalculate again, all right? So we need to have some strategy to calculate the effective width of that section, okay? Now I walk you through that. So now this is where we calculate the effective section modulus at this stress, okay? Now next one, I will walk you through how to calculate the section modulus of effective area of the beam, but with the stress here equivalent to the maximum F star. So exactly the same procedure. You just replace F star equal to 450, replaced by whatever you go calculate here, FC. Okay. Now I just work it for you, step by step, to go to calculate the effective width. Sorry, the section modulus for effective width section. Okay. Now, as I mentioned before, this is the beam. So we have neutral axis lie somewhere below the symmetric axis, and you can see we need to break it down into different elements. And whatever element on the bottom here is the intention. So it means it's fully effective. Nothing to do with buckling, right? Buckling is when we talk about compression. So from neutral axis up to here, then it's problem maker, right? Because in here we need to remove some useless area where it's buckled, and that's why, and remove those one, okay? And then we calculate. That's how we're gonna do. Right. For flange and for lift, because of bending, which means that the top flange and maybe the lift we can consider is purely compression, because it's very small. We can assume that this stress is uniform, so we can assume that the flange and the lift is in pure compression. All right, and then we come back to our previous calculation, exactly the same. We can calculate B1 and B2, and we can remove the area, and we can calculate this one, and we can calculate and remove the area. We got an effective width. Now, right, so we do it, okay? So I'm not gonna spend more time to repeat it, because you're gonna follow exactly the same procedure for the flange, and then for the lift, and then exactly the same. We calculate the lift. But interesting in this section is the lift is not fully effective. So you can also, lift is fully effective this way. Okay, sorry. It's because it's less than this one. Okay, so exactly the same with the one that we calculate in the column. Then we can calculate RS. Then I move to the flange plot, and we follow exactly the same. We calculate B on T, and we calculate S, and then we put in this equation is smaller than that one, and then we can we say that the flange is not fully effective, and we can calculate K. And K here is 2.26, right? It's in the middle somewhere between 0.43 and 4. And then we can calculate DS, and then eventually we can calculate the rho, how many percent of the top flange. And you can see here, only 60%, 61% is effective. So we have to remove about 40% of area, which is hopeless, which is not good. All right, so this is based on effective width. We can calculate that. Now, the problem with the bending, with the web. So we don't know exactly where we can calculate. So firstly, we have to assume that now the web is fully effective, right? So it means that if we split that one out, the neutral axis will be right in the middle, okay? And then we got a top and the bottom stretch distribution is equally. So that's what. So we got that one. We assume that one first, and we put that one into this equation with the fully effective area, but this is effective area. Then we calculate against Ix and Iy and everything that we follow at the beginning, exactly the same what we did, all right? So, but based on the assumption that the web is fully effective. Then we do it. Then we can calculate the new neutral axis in here. It's not right in the center anymore because the top and the lip is missing some area. So that shift a little bit down. You see here? 109 instead of 100 sometimes. So this is based on the assumption that the web is fully effective. Right, and then we calculate again. Then we check. Now, is the painful things now is coming in. We don't know exactly the new one, neutral axis is. So we just try and error. So first we pick up one, like 113 or something, below the neutral axis. And then we start to play around. And then we follow the equation in the standard. And then it will give you the equation to calculate BEW2 and BEW1. All right, based on our assumption on that. So now we have a new section with that removal of area with the assumption that we made at the beginning. Then we can calculate again everything. Not everything. The top and the top flange and the lip is we done already, so that we don't have to worry. But the web we have to do it again. So you can calculate BW1 and BW2, and we got that. Now we put it back to our equation again, not equation to calculator again. Then you can get that new one. So actually 113 is the one that the final loop, the final iteration that I choose. So that's why you got that one matching with what you got at the beginning. But at the beginning, you don't know exactly where it is, so you have to play around with that. So in terms of design, I think it's not really difficult for you if you just put everything in spreadsheet, right? Just change it and then drag it, and then you can get calculation. You can do a calculation quickly. But the procedure is complicated, as I say, and you need to do a bit of iteration until you get this one. And that is exactly where the neutral axis of the effective width area. Right, so then from that, you can calculate the ZEX in here, all right? And that ZEX, that's the one that we need for section capacity, right? Not about the one in here. Sorry. This one? No, okay. Okay. Let me come back to what I'm talking about. Is here. Okay, not this one. Okay. The ZEX that we work it out from that one is different this one. Yeah, why is different? This one is effective section modulus when F star is equivalent to MO, MS equivalent to FC, right? Yep. But the one that we just done, it means that we calculate FC equal to FY. So that is slightly different. Right? Procedure is exactly the same, but you need to work it out two effective section modulus. One is that one when the buckling stress is at FC. And the other one is exactly the same, but when you calculate with the buckling stress equal to Fy. So that is the difference. So this one, when you calculate the member capacity, but when you calculate the other one that we done, so we can calculate the section capacity, right? So in conclusion, that I want to share with you the summary of how you're gonna do it. So first is you calculate the elastic buckling stress, all right? So that is M naught equivalent to MOC on column. And then depending on the lateral restraints and everything, boundary condition or whatever, then you can calculate FC here, MC here. And MC is equivalent to FC in the column. And then from that, you need to calculate the effective section modulus, ZCX, which is equivalent to AE effective of the column. And from that one, you just calculate the bending capacity by timing with the FC, and that's it. So just follow the same procedure. The only thing that different is this guys, all right, effective section modulus, where you can straight away calculate based on effective width area. You need to make some assumption, and then we need to work it out a couple of loops, a couple of iteration until you get the right position of neutral axis, and then you can calculate that. Okay, so with that, I conclude the lectures on effective width. I hope that I give you a bit of general understanding. Some of you working on effective width for already, so probably a bit too much. But for those who are not familiar with the effective, I think I put a bit of fundamental and equation. So hopefully that you can follow that, and then come here. And when you go home, just try to go again. Put some draft paper and put some equation and work it out by yourself, and then I think by that way you can understand all that equation. But in general, that is all the procedure that we need to do. Okay, so other than that, thank you. Any question? Yes?
So when we provide that slash box, so is that extremely restrain the LTV because it is connecting to the bed. We need to connect it to the flange, right? So in order to completely arrest LTV.
Very good question. In Australian standard, we have the factor KL or KC not in AS 4600, but in AS 4100 for hot roll steel. Depending on the position of lateral restraint, you can put on the top flange or bottom flange or whatever, then it will affect the buckling capacity. So normally you put a factor 1.4 or 1 or 1.2, depending on the position of that one. So of course, when you put on the top flange, it buckles this way. It's better than you put on the top, on the bottom. It twists like this one, right? So that's why it depends on the location of the lateral restraint. The standard will give you a different number, and you can just plug in. But it's a very good question. So it doesn't mean that you plug in the middle anywhere and you get the same. Of course, depending on the position, and you can provide more restraint or less restraint depending on the position. Yeah. Yep.
The example.
Yep. Can you put that one back? I don't know why. Okay.
The example in the beam, you have taken the example of purling.
Yes.
Actually, purling is asymmetric building.
The purlin.
It's an asymmetric building.
The purlin that we choose here is C section, is singly symmetric section.
No, sir. I'm specifying the direction of load applied on the section.
Okay. So we assume that it's the wind uplift, so it's perpendicular to the section.
Under the wind, it is a beam. For dead line loads, it is access number.
If it's going down, if the wind, if the load is the wind, gravity, so it is not purely. Yes, it's another problem is biaxial bending. You're right. Yeah, what we call is biaxial bending. So it's back this way and a little bit of the other one. So it's actually very interesting.
The load line is also not along any of the axis in the case of gravity loads.
Yes, that's
Section axis is not coinciding with the direction of the load. In the case of gravity,
the gravity. We assume that the load acting through the centroid. Huh? But in which channel section is a little bit problem. The shear center is offside, so there's another problem coming up too as well. So as you say, that is more complicated. But what we decide just simply wind upload. We assume that the load is wind upload. So with wind upload is perpendicular to the what we call is principal axis. Right. So I got your point. I have one of my PhD now working on biaxial bending. We hope that we can do. It's not just about purlin. About the column as well. If the corner column channel section, when you got wind this way and you got wind this way, so actually the column subjected to the biaxial bending, and of course with the compression action as well. Very complicated in that way. Yep. So your point is very good. In the case, we got a couple of papers on the storage rack. Storage rack, the C section. In the practice, sometimes they don't make the wall. They just attach something on that to make the covering, and that when is subjected to the wind of two direction, and that upright or that column will subject to biaxial bending. Yeah, and then it's subject to very complicated load cases where it's combine a bit of this, combine a bit of that, and combine of the compression. So we need to look at the combination or the interaction. So it's ongoing. I hope that we did some testing, come up with some equation later on, and we can share with you. Very good question. Thank you. Yes, any question? And just on this one, when you design Z section, it's more complicated as well. So at the moment, for Australian standard, we assume that Z section is C section. We just put it equivalent and design for that. Yeah, but Z section, as you saw now, is point symmetric axis section. And to calculate buckling load is a lot more complicated. We don't have a model now to calculate accurately. So that is the first one. And the second one is the strength as well. Yeah, because when it buckle, this side is different and that side is different because the lip is going down. It's more compressive stress acting on that. So a lot more complicated. So we're trying to understand it and get some testing. So we build up the test rig to test that one already for channel section and Z section subject to spectral torsional buckling in Sydney Uni, and we can see a lot different. So it's not just equivalent. So we need to learn something more, and but of course that's part of research, right? The more we learn, we know. And we put it back to standard. Hopefully next 5 years, 10 years, we're going to have a different equation based on our new research. Yes, any question? So, good news is from tomorrow, everything is going to be a lot simpler. Everything is clear, everything exciting. It's not painful like this one. You got to calculate 100 of equation and all that effective width, cause you a headache, right? Yeah. So now from tomorrow, we're gonna learn something exciting, right? So I look forward to sharing with you, particularly for tomorrow direct strand method, which I'm involved very heavily, and then I'll share with all my passion to you. Thank you. Any question? Just feel free to ask. Okay, I'm still around. Thank you. By the way.